Liquid is dense, heavy, and notoriously stubborn. Yet modern civilization depends entirely on moving oceans of it every single day, from drinking water to raw petroleum. The most intuitive way to move fluid is to force it. Positive displacement pumps do exactly this by trapping a fixed amount of liquid inside a sealed chamber and physically squeezing it out. But the machine responsible for the vast majority of global fluid flow takes a completely different approach. The centrifugal pump doesn't trap or squeeze water at all, even when mounted to a fire truck pushing massive, continuous streams at high pressure. To move this much liquid without trapping or squeezing it, the pump relies on a continuous chain of energy conversion. Pushing heavy water uphill against the drag of gravity and pipeline friction requires an energy relay. A single baton of energy must change states 4 distinct times. Inside the casing, energy shifts from electrical to mechanical to kinetic and finally to hydraulic. We can actually track this process by following a single unit of energy, starting from the power wire entering the machine all the way to the high-pressure jet leaving it. If any single handoff in the sequence fails, the underlying physics break down entirely and the entire system collapses. The relay starts at the back of the machine, completely isolated from the water, where alternating electrical current feeds into the motor. That electricity flows directly into the stator's copper coils. As the current cycles, it generates a powerful, rapidly rotating magnetic field. Because the magnetic field is constantly shifting, it induces a current inside the internal rotor sitting at the center of those coils. The invisible magnetic force physically grabs the rotor, forcing the attached steel shaft to spin up to speed. The first handoff is complete. The energy is officially mechanical. But a spinning rod of solid metal sitting in an engine housing does nothing to move water through a pipeline. This technical cross-section shows the next stage. The shaft reaches out of the motor, pierces the pump casing, and bolts directly to the impeller. As the impeller spins, it creates a low-pressure zone at its center eye, drawing liquid directly into the core. Once inside, the curved vanes catch the water. Through centrifugal force, the fluid is accelerated and thrown radially outward toward the outer edges of the disc. The impeller might have an open design for passing debris or a closed design for clean water, but the goal is identical: accelerate the mass of the fluid. Because the water is now moving at an incredibly high velocity, our energy baton has been passed to state 3, kinetic energy. But raw speed is not effective for moving water over miles of rough pipe. This reveals a central constraint in fluid transport. Fast-moving water is not the same thing as high-pressure water. To push liquid upward into a water tower, we need static pressure, not velocity. This animated diagram reveals the solution: the volute casing. It's a spiral housing surrounding the impeller that is specifically designed to get wider as it wraps around the pump. When that high-velocity, kinetic water flies off the edge of the impeller, it immediately slams into this expanding volute area. According to Bernoulli's principle, as a fluid's flow area expands, it is forced to slow down, and when the velocity drops, the pressure increases. By deliberately forcing the water to slow down, the pump pulls off its final trick. It trades this kinetic speed for the immense hydraulic pressure required to successfully push heavy fluid against friction and gravity. Because this machine functions entirely by manipulating extreme pressure changes, it operates right at the edge of a physical threshold that can turn catastrophic. If the incoming pressure drops too low at the center eye of the impeller, the laws of thermodynamics take over. The water will boil into vapor at room temperature. This diagram sequence shows the consequence. Those newly formed vapor bubbles are thrown into the high pressure zone, abruptly collapsing. This is cavitation. They don't just pop, they implode, firing a supersonic microjet of water into the surrounding metal like a microscopic jackhammer. Millions of these tiny implosions happening over hours or days will eat away solid steel, pitting the impeller blades and destroying the machine. Cavitation reveals the complex engineering required to maintain this flow. The system only functions because it maintains a precise, narrow window of fluid dynamics. When calibrated correctly, the quiet exterior of a facility like this hides millions of energy transfers happening every second. The invisible relay completes its cycle. Electrical power drives mechanical rotation. Mechanical rotation creates kinetic speed. Kinetic speed expands into hydraulic pressure. And throughout that entire process, the pump never once traps or physically squeezes a single drop of liquid. It achieves the massive continuous flow that keeps civilization alive simply by bending the laws of physics to its